Morning, everybody. So today what we want to do is to talk about a new type of X-ray fluorescence system that is using grazing angles with energy tunability, specifically more for geological applications. So what we want to do is to start off with what is this next generation type of X-ray fluorescence systems to do elemental composition, because currently when you look at the elemental compositions, you can use many techniques like XPS or TOF SIMS or EPMA and conventional XRF for geology and metrology. But the drawback for many of the X-ray techniques is you have very limited sample depth, and also sample sizes in many cases needs to be small, and also it can be destructive and non-quantitative. So what we want to talk about is a type of novel X-ray fluorescence system that give you the advantages of the XRF in synchrotron, that gives you ability to look at variable sample depths up to several hundred microns. This means you can study not just surface minerals or elements, but also things that are subsurface, and which is non-destructive and that is quantitative. And it has spots that are comparable with SEM and EPMA. And it has the ability to look at low Z elements like carbon, oxygen, nitrogen, phosphorus, sulfur, sodium, aluminum, things that are normally not easily detected at low concentration. So what is and who is Sigray? Our mission to bring synchrotron X-ray techniques to the laboratory. Because if you take a look at existing laboratory X-ray techniques, whether it's XRD or XRF or XPS or XAS or X-ray microscopes or XAS, you find that many of these techniques are offered in the synchrotron, and there are many researchers that will go there because there are limitations in laboratory techniques. For example, limitations in terms of the poor source brightness, and also the poor flux that gives rise to lower sensitivity. This means if you have very dilute concentration or things that are in the ppm or sub-ppm level, you would not be able to detect. And also they go to synchrotron to get better optics, because synchrotron can focus the X-ray beam into a smaller spot size, and you can get better resolution. Also, most importantly, in synchrotron, you can select the energies that you want that will be optimized for the characterization of that particular element. A little bit of Sigray's background. We are located in America, in the San Francisco Bay Area in California. Our founder and the CTO is Dr. Wenbing Yoon, who formerly founded an X-ray microscope company that, because it has been so successful, it has been acquired by Carl Zeiss. So we have several patents, and our mission is to bring next generation X-ray techniques to the laboratory. So what are the innovations that is possible in laboratory X-ray source and optics that can bridge the gap between the X-ray techniques in synchrotron versus what is available in the lab? In order to have a performance that will be closer to synchrotron, you actually need to improve your source brightness, because technically the laboratory X-ray source is less than 1,000 of that of the synchrotron. This means the synchrotron light source, the X-ray source, is at least over 1,000 times brighter than the lab. So to do better techniques in the laboratory that has better performance, first of all, the X-ray source must have an increased source brightness. Next, the synchrotron has the ability to focus X-rays. So the laboratory likewise must have the ability to focus X-ray to a smaller spot. Then the synchrotron have a choice to choose different energies for their analysis. And to get something that is close to the synchrotron, now you have energy tunability. So the good news is our company have been able to solve all three problems from the source to the optics to energy tunability. So we created an X-ray source that's 30 times brighter than conventional micro-focus X-ray tube. And also we fabricated optics that is used by the synchrotron that is 10 times higher efficiency than the typical focusing optics like KB mirrors in the synchrotron. And he has the ability to also to get smaller spot size. So by combining our patented energy tunable source, what do you mean by energy tunable source? This means one source, X-ray source, can give you different energies. Like it can give you energy of copper, give you energy of silver, or give you the energy of tungsten. So multiple energies in one tube that allow you to change energy as and when you need them. So with this combination, by combining the X-ray source and the optics, now we have been able to come up with a suite of products like microXRF, that's what we're going to talk about, that is having performances very similar to XRF in the synchrotron. We also have an X-ray absorption spectroscopy that is used for battery and catalyst research. We have X-ray microscopy from the nanotechnology side all the way to the conventional X-ray microscopes. So what does the AtomMap X-ray fluorescence system do? It has the configuration for the next generation type of equipment that you may be interested in geological application. For example, our source or X-ray tube or anode has an energy tunability. It has the ability to look at like elements. This means it can go and analyze very low concentrations of even like elements all the way down to boron. Then it has the imaging resolution. This means the spot size can be 3 to 5 microns. And it has sub-ppm sensitivity, and it is flexible and customizable. Let's take a look at some of the innovation in X-ray source or X-ray tube technology. Generally, when you are trying to make an X-ray tube, these are the principles. You have a filament that will give you a charge of electrons, a charge cloud of electrons that is accelerated in a potential difference. This means the potential difference will draw the electrons to accelerate to bombard against a metallic target. So as the electrons bombard at a high energy into the metal target, it is changing the kinetic energy to a heat energy. So it starts to heat up the target. So more than 99% of all the energy is converted into heat. Less than a fraction of 1% will generate X-rays. And these X-rays are generated in all directions. And if you want to have higher brightness or higher flux from the X-ray tube, then you will need to increase the power loading. However, as you increase the power loading, you are going to increase the heat. So as a result, not every X-ray tube can increase power loading. In fact, there is a limit. Like for example, if the power loading is more than 1 watt per micron square, the metal will melt in the X-ray tube. So therefore, there are not many metals that can be used to make X-ray tubes. So how do you solve this problem? We created a patented X-ray tube that embed targets in a thermal conductive material, and simply because you want to get rid of the heat energy. So the the substrate that we embed into is diamond, because diamond has 5 times the thermal conductivity of copper, so that whatever heat energy is created, it is now quickly dissipated away. That gives us the ability now to have higher power loading. When you have higher power loading, now you have more brightness or more flux in the X-ray tube. So why is this important? So we came up with this tube that has all these targets. So we look at it and say that, okay, instead of just putting a row of metal, maybe you have a tungsten target. So you have a row of tungsten target that is embedded in diamond. Then why don't we also put another different material? Like, for example, we can do chromium, or we put another row, we can do silver. Another row, we can do, let's say, tungsten and various other elements into the same X-ray tube. So in other words, when we move our electron beam to just focus on a particular target, it will give you a specific X-ray energy that will help you to optimize the analysis. So having a tube that is higher brightness, 30 times brighter, now having multiple energy capability or multiple targets, and using an optics, we can now have very focused X-ray spot size, so that you can do very precise imaging on a particular region of interest. Then you will be able to come up with a tunable X-ray tubes. For example, some of the choices of metals or anodes that we can use is tungsten, rhodium, molybdenum, gold, copper, chromium, and silver. So those are the materials that we can put into this X-ray tube. So we can put up to 5 targets. This means now we can switch energies to 5 different energy range. Why is this multiple X-ray target important? Is if you take a look at this chart, for instance, if we were to look at analyzing aluminum, a soft material. Now, if the fluorescence cross-sectional yield, these are the numbers here, shows that if I were to use a molybdenum tube that has the energy range of 17.4 kilo electron volts, we may only have a 5 counts in the fluorescence cross-sectional yield, or maybe the counts in the detector, you can say that. But if we were to change to copper, now my count rate is 10 times higher than molybdenum. What if we are going to do chromium? Now you're talking about the 30 times more. But what if you're going to do a silicon source? Now you are talking about more than 644 times increase in the count rates, or in other words, you will be able to detect and count how much aluminum is that in the sample, and be able to do quantitative work there. Let's take a look at why or how we would use the ability to switch energy for geology. For instance, if we are looking at a mining target, this means we are looking at a rock that has gold, but then the gold mineral is very, very rare. In fact, the native abundance of gold is around 1 ppm. That means 1 parts per million. So if I'm going to look for something that's 1 parts per million, it will take a long time. They call it like searching for a needle in the haystack. So that is not going to be helpful. So what we want to do is, if I want to search for gold, I do not just look for gold simply because they are so rare. So what we want to do is that, can we search for gold with the associated elements or associated minerals that the gold is normally found with? So for instance, arsenic will be one of those candidates where gold is normally associated with. But if we were to try to scan the sample for arsenic, which has quite a high abundance in that particular rock, uh, and if we were to use tungsten's target, the arsenic is not what you call activated or does not fluoresce. So therefore, you will not see arsenic using a tungsten target. What if now we change the the target of the X-ray source from tungsten to molybdenum? You find that molybdenum now have the ability to excite arsenic. In fact, the whole sample lights up like a Christmas tree. You see that these are the regions within the grains that is rich in arsenic. So what we are showing you is by switching energy, that means having energy that's tunable, you'll be able to detect things that are normally not detected if you just have one single energy. So let's take a look at another example. The other example is this rock. If I were to use a molybdenum source or molybdenum X-ray target, as I scan this, if I scan for iron and make this red, so therefore everywhere you see iron will be mapped out as a red patch. And then if I want to look at the potassium, the green thing will come out. So everywhere is green. Now shows this is the regions where potassium is found. So in this particular sample, you see the yellow dots or yellow map. That is because the molybdenum can excite bismuth within this sample. So everywhere you see yellow, there is that is where the location of bismuth is found. Let's take a look now. What if we change the molybdenum source and change it to copper source? Using the copper source, the iron doesn't seem to change because what you have found in this sample using molybdenum source is also replicated in the copper source. What you found as potassium in this sample is also found in this particular sample using your copper source. But guess what has changed? Using the copper source, it does no longer show the evidence of these yellow specks or the bismuth. Not because it is not present, it is present, but because copper source will not be able to excite bismuth, but you see the blue dots. These are the silver particles. So we have seen silver using copper source, but we did not see silver using the molybdenum source. So there's a power of being able to switch from one energy to the other energy to see things that cannot be detected. So this is the patented AtomMap X-ray source. So within one source, we can put five different target elements of 5 different energies, and you see that all of them have different characteristics line. So now let's take a look at how do you get a microXRF. MicroXRF means that now you have a spot size in the XRF that is in the micron range. That's why they call the micron or the micro XRF. So traditionally, when you use a single X-ray tube without an optics, you find that your spot size can be several millimeters in diameter, just like when you look at the XRD spot, the XRD spot can be several millimeter in diameter. So micro XRF makes use of the principle of polycapillary optics. It's a bunch of fiber optics. That means it's a glass capillary optics that has been fused together in a bundle, and that's why they call this a polycapillary optics. It has a capillary optics, and how it focus a X-ray beam is not real focusing. it is just by the reflection or multiple reflection of the tube that is curved. So this means it will bounce and bounce, that comes in and goes out. So you can see that because of the multiple bounce before what is coming in from the source come out to the side here, the efficiency of this type of optics is only 5 to 10%. And also the point spread function is about 20 microns. In other words, no matter what you do, you will not be able to easily get to a spot size of less than 20 microns. So that's the way microXRF tubes are configured using a polycapillary optics. But for and also using these capillary optics, your working distance is going to be very short. Yeah, when the working distance is going to be very short, this means there's a chance for you to hit the sample on the detector and so on, causing some problems. So let's take a look at what the Sigray optics is all about. It uses a twin mirror optical lens that is used typically in the synchrotron. And in this particular configuration, the efficiency is about 85%. The point spread function is 3 to 5 microns, and you can have a large working distance. So what are the results comparing a polycapillary optics versus the true optics that is used to focus X-rays at high efficiency? In the polycapillary optics, you find that the energies that is coming out from that tube over here is based on what is the energies that is coming out. So, like for example, the low energy will become a bigger diameter. The higher energy will become in the center. So you find that when you analyze a sample using this capillary optics, you do not know what energies are hitting it, and therefore your quantitative measurement is very difficult to predict. So this is what happens. When it's high energy, the depth of penetration on the sample is higher. When it's lower energy in the circumference, then it is wider. Whereas using a true X-ray optics, now everything is the same diameter. This means the spot size is the same for all energy. So this is what we call achromatic example, whereas the polycapillary do not have these achromatic examples, because the spot that comes out from the optics are very energy dependent. So that's why, as a matter of comparison, most people who are using polycapillary ends up with a spot size maybe about 20 to 40 or 50 microns. But using our optics, you can get it down to less than 3 or 5 microns. These are the proof of resolution. You can see that we can easily resolve the 5 micron line in this calibration sample. So X-ray fluorescence is a technique that allows you to detect multiple elements throughout the periodic table of your sample, and is a non-destructive technique. And if we want to look at, let's say, different type of equipment as to what is the ability of each equipment to do trace level elemental analysis. So this is a chart that is given by one of the largest service provider in the world, that's Evans Analytical Group. They have all kinds of X-ray equipment, and you will be able to use their services, and they put out this chart. This chart shows you that, okay, between the different equipment, what is the detection range? This means 100%, all the way to parts per million, to parts per billion, to parts per trillion. So what equipment will fall under that category, and what spot size are you working with? Whether it is a 1 centimeter spot size all the way to micron spot size all the way to nano systems. Now, like for example, if I want to look at, let's say, SEM EDS, for instance, that's where most of us use SEM EDS for elemental composition. You find that if your sample or concentration of the elements is a sample is not higher than 1%, in general, SEM EDS will say that no such element exists. Is it true that no such element exists? It's only because your SEM EDS cannot detect anything that is smaller or more dilute than 1% atomic weight. Now, if we are looking at, let's say, TEM, right? You have TEM, you can actually get a smaller spot size like STEM EDS will give you the ability to get a spot size down to nanometers, but then your concentration, the best is about 0.1% in order for it to be detected. Now, to do trace level analysis, let's say that's less than 10 ppm, there are not many tools that you can use. One of them you can use is the SIMS. The other one you can use is the wet chemistry method known as ICP-MS, or using TXRF. So you see that not many equipment now will be able to do trace level analysis. So if your job is to look at some of this trace level analysis, it becomes increasingly difficult for you to do. So typically, people will have to use wet chemistry techniques like ICP, or you have to use SIMS that gives you good detection level. So where does the AtomMap comes in? It comes into these areas that you can go all the way to high concentration and all the way down to your sub-ppm level, it can detect. And this is a non-destructive technique. So just as a matter of summary, this is what happens. Now, if we have the typical tool like SEM EDS or XPS, you find that the problem is the detection level has to be 1% or higher. And it is not possible to look at low Z elements like carbon, oxygen, nitrogen type of application. Or you can go to EPMA. EPMA gives you better detection level than your SEM EDS, but the sensitivity is around 100 ppm. And for low Z elements is going to be very challenging. EPMA will be very sequential. That means you can only measure one element at a time. So it's very slow and it only measures the top surface layer of just a few micron at most. Then the next one is if you want to look at sub-ppm level, you go into ICP-MS, but then the detection level is good, but you have a lot of matrix effects. In other words, you need to match the standard to the real sample. And it cannot detect low Z element like carbon, oxygen, nitrogen, fluorine, and bromine. SIMS detection level is in parts per billion. It has small spot size, but the analysis is slow, and also you have matrix effects. So where does that leave you? You can go to the synchrotron and do microXRF that will have the ability to go to sub ppm level concentration and is non-destructive, or you can get the laboratory AtomMap where we can simultaneously look at multiple elements using a small spot size to look at sub ppm level. We can operate in vacuum or ambient. You don't need a perfectly flat sample. You can look at low Z and is non-destructive and is fast and non-versatile. So before we go on to some of the applications, let's take a look at some trace level analysis if we were to use ICP-MS. When we use ICP-MS, one of the problems is the low Z elements and many other applications, you do not have good solution using ICP-MS. In fact, to solve that problem, what we have to do is, and why is that so? Why is it so difficult to analyze using ICP-MS is because there are a lot of polyatomic interferences within the transition element. And also for carbon, oxygen, nitrogen, it has very low ionization cross-sectional yield. So as a result, it's not easy to analyze that using ICP-MS accurately. So carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine are difficult or impossible using this ICP-MS. So what about AtomMap versus EPMA? AtomMap give you the advantage is because it can vary the angle of incidence using a goniometer. EPMA only excite the depth of 1 to 3 micron, and the AtomMap has a comparable spot size about 3 to 5 microns, and we can do sub-ppm level sensitivity. And there is no need for sample preparation using the AtomMap. And also you can run it with vacuum or without vacuum. Whereas with EPMA or the electron microprobe system, you need to, it's like an SEM. You need to run it at high vacuum, and also your sample needs to be polished and needs to have a coating in order to conduct away the charges from the electron beam. So you can see that what are the difference between running with the electron excitation versus with X-ray excitation. Now you see that with the electron excitation, the spectrum, you have a very high Bremsstrahlung or very high background. So therefore your background is high, so sensitivity is going to be low. Whereas the rate spectrum is from the X-rays. You find that the background is low, therefore it has been able to see detection levels that is much better than in electron optics excitation for fluorescence. So as a summary, the AtomMap has 3 to 5 micron spatial resolution. EPMA, the spot size normally is 2 to 3 microns. Sensitivity is in sub-ppm. Sensitivity in EPMA is hundreds of ppm. And AtomMap can measure 30 to 50 elements at one go very quickly. Whereas EPMA, depending on how many WDS detector you have, you can only be limited at 4 at a time. And the analytical depth, you can go down to 1 micron to hundreds to maybe several hundreds of micron, and also the throughput gain compared with EPMA is at least 10 times faster, and there's no need for sample preparation, nor having to coat your sample with a conductive layer using the XRF. So there are two models in the microXRF system. One is the ambient system. This means it's run in normal atmosphere. The other one is a vacuum systems that can rotate or tilt the samples at the glazing angle. So many applications are possible. Besides geology, you can do semiconductor like thin films, contaminations, failure analysis, or for biology, in metallomics, or in material science, or in battery research, everything. So the microXRF is very versatile. It can support your geology plus any other applications using that is requiring elemental composition. So here's an example of our XRF compared with the results from the synchrotron. These are the results of the laboratory-based XRF compared with what we see in the synchrotron. This is measured in the Australian synchrotron here. This is measured in our system. And here is an example of a plant where we are looking at the iron concentration or looking at zinc concentration. You find that the results that we have obtained with our lab system is even better, according to the customer, even better than what they have obtained in the synchrotron, including the ESRF in Europe. So this is also another example. This is done in ESRF. This is the Daphne or the water flea. This one is done years ago when we first came out with our product. Not as good as synchrotron here, but then we can still see many of the structures, including the eggs within this water flea. Our system is currently used by the top tier semiconductor companies like Intel, like TSMC's, to look at the advanced semiconductor metrology. And in fact, we can look at the low level of detection of thickness change down to a fraction of 1 angstrom. There's 0.03 angstrom, and we can plot the calibration curve there. In geology, you may want to scan large samples. Here is a sample that's 100 millimeter by 100 millimeter, and you're trying to look for rare earth elements. How are you going to do that? So we can quickly scan. In fact, every point that we scan, it is about 5 milliseconds. So we can quickly scan and give you all the elemental compositions within the sample, and you can now further zoom in and which area in order to do analysis. We can also look at the roots, like in this case is a cypress root from Israel. That shows that when the drought comes, they will give off some root exudation. This means small rootlets are coming out in order to protect them during drought. And also these are the GMO type of leaves to look at different elemental compositions. And if you try to look at the SCM, you cannot do elemental composition on leaves because those concentrations are in the few ppm range and is out of the range of SCM EDS. Here's another example to look for rare earth elements, like for instance, yttrium, which is in yellow. We'll be able to scan the whole rock and tell you where the yttrium is distributed. A little bit about how do you analyze low Z or low Z elemental analysis using XRF. Now, here you can see that if you have a lower primary X-ray energy, you find that you have more fluorescence U for low Z. Now, if let's say X-rays were to hit this sample, and if I have, let's say, oxygen or nitrogen that's buried here, so you have a concept known as escape depth. So because the energy of those low Z elements are very big, it has to be strong enough to be able to escape the depth. So many of them would not be able to be detected unless it is surface. So that means those low Z elements has to be near the surface before you can even detect them. When it's too deep, it would not be able to affect the escape from the escape depth, right? And low Z elements also require vacuum path. That means there must be a vacuum so that the fluorescence is not going to hit against air molecules or nitrogen, and therefore it doesn't reach the detector. So let's take a look at the low Z and vacuum. Low energy X-rays get attenuated or get knocked or prevented from hitting the detector by the air. So by removing the air to get a vacuum, you will be able now to start to detect carbon, nitrogen, oxygen, fluorine, sodium, manganese, and magnesium and aluminum. And so you see that the amount of X-ray transmission in the air is depending on the energies, and you find that when you have lower excitation energy, basically there's no transmission because most of the fluorescence will be blocked by the air molecules. Why we can do low Z elements is because the standard XRF configuration shows that the X-ray beams is incident to the thin sample, and it does not excite a lot of area. But if we were to tilt the angle to even grazing angles, we will be able to improve sensitivity and also the sensitivity of those low Z elements, because now it can overcome the escape depth. So the variable energy or variable angle will allow increasing region. This means it's a larger region you can access, and also the depth of interaction increases the sensitivity, especially when you're looking at thin films and low Z elements. And also you can avoid diffraction peaks. In XRF, there are things like diffraction peaks that will make it difficult for you sometimes to do quantitative analysis or positive identification of some elements. But by tilting the stage, you now can avoid the diffraction peaks. So here is an example of the internal of the system. You can see that you have detectors, and also you have goniometer there. Now, okay, what are the advantages of the Sigray systems for low atomic energies? Is it has a unique X-ray source because we have multiple X-ray source. Therefore, it can increase sensitivity for certain low Z elements. And also we have a high efficiency optics compared with the traditional microXRF. We now have our own optics that gives you very high efficiency focusing, and our vacuum chamber, it is in a high vacuum regime, 10 to power -5 torr, compared with other systems in the market where the vacuum is only 1.5 torr. So here's an example of geology using fossils, where we want to look at calcium, aluminum, oxygen, as well as phosphorus. With the different color coding, we can see this fossilized fish has also the purple color is the oxygen. Right. So this means there are a lot of oxides that is covering this fish. There is little to no sample preparation required, and the sample size is 200 by 200 by 25 millimeter. So let's take a look at mineralogy. All right. The system will also have the ability to study mineralogy. Like for example, we can map different elements for titanium. This is iron, there's potassium, magnesium, sodium, and the other one might be oxygen. So you can see that the blue one is the oxygen, the green one is the magnesium, the red one is sodium. So many of these are low Z elements, and we can detect them quite easily using our system. So to do a test, we bought a set of geological standard minerals from Ted and we just run it, and we have been able to identify the majority of these minerals using our software. Right. So there are publications using our system, like this one is publications that is using our AtoMap and EPMA. That is published in 2023 of this Journal of Petrology. So in geology, a lot of times you use optical microscope. So here's a picture of this section of this piece of rock using optical microscope. Here is the section of the analyzing using SEM EDS. And here is what the AtoMap is capable of doing. You can see that not only can it identify different elements, it can map at high resolution. You can see see the striations or the variation of the color showing different concentration. And you can also study your existing microscopic slides, your geological sections, and reanalyze them, because this one are normally done by staining, but we will be able to analyze it directly and come up with the concentration or the distribution after we have done our peak fitting. So here you can look at compositions in terms of weight percentage of the different minerals, and we can do this under standard or under standardless analysis. Another example of geology is, let's say, volcanic rocks. In the volcanic rock, we see that we have we have a regions that is at the rim and also at the transition region. And so let's take a look at the region of interest. This is a core, and this is a transition, and this is the rim. So you can see that the heat map of the rim and the transition shows that they are different type of structures depending on which region of interest that you are looking at. Here is the rim and the transition. You have different type of structures, whereas here is the core, and the different elements are also shown. So here is the transition region, and versus the rim region, you see that the iron, which is the blue color, seems to grow along the edge, right? More of the edge, whereas those in the middle of the grain, the iron is in the middle for the one that is in this rim region. In geology and mining, for example, gold mining, a lot of times we deal with what you call gold that is called invisible gold because it is so small that you cannot find them. So this is a technique where we are also able to try to look for invisible gold in the rock section. A lot of times when they look at the rare earth minerals, sometimes they want to see the hyper accumulation of minerals, certain minerals in specific plants. So here is a plant called Saxifraga, which is used to be able to accumulate rare earth. So some of the work that has been done in the synchrotron, they send these samples to us using our laboratory system, and the customer says that our results are some are comparable, but some of them are even better than what they have obtained in the synchrotron. And as a result, that professor bought our system. Right. So these are all examples of the rare earth, the zinc, the iron, the calcium, the aluminum, phosphorus, sulfur, and potassium. So all of them will give you the map of the elemental composition that match the studies that they have done in the synchrotron. This system will also be able to look at environmental remediation, like for example, in the mine that has been disused. What happens is that in the mining operation, many of those earth or the soil that is deep on the earth is now put up to the surface, and many of them are toxic, many of them are radioactive. So humans will not be able to healthily live on the land that has been used for mining. It may be maybe over 100 years before they can be reused. So to solve that problem of quicken the detoxification, you can plant certain plants that specifically accumulate some of these toxic minerals, in this case like cadmium. So you can see that by planting this type of grass, cadmium, this is in blue, can be concentrated mainly on the root area. To conclude, I want to talk about decarbonization of steel. This means, can you measure iron quantitatively? So with all the things that is pushing by certain governments to do to affect or decarbonize, like for example, steel industry give off a lot of carbon dioxide emission. So many governments are forcing some of the steel mills to reduce the carbon content in their processing and limit their emissions into the atmosphere. So they have to come up with methods in their processing of the steel that uses or produces less greenhouse gases like carbon dioxide. So here is a situation where we have been successful to help companies like steel companies or even the university find ways to absorb carbon dioxide from a certain process or from the atmosphere. In this case, we have been able to look at carbon. How do you measure carbon content in steel? That is not easy because the carbon is in pretty low concentration. In this case, it is like in the fraction of less than 1%. We have been able to do that and measure and calibrate that, looking at the carbon content of different steels. As a result, now we can do this project that if you change certain processes, what is the amount of carbon that's left over? And the same team happens to how can you sequester or absorb carbon dioxide from the atmosphere. So one particular candidate is a certain type of concrete that because there's so much cement that has been used, you can actually see if certain type of additive can absorb carbon dioxide from the air and take it out from the air. So if that can be done, then now you can set up a calibration curve and be able to quantitative measure carbon content in different materials as part of your research project, because many governments want to give off grants for those who are doing environmental or climate change project. So in conclusion, there are many challenges in doing non-destructive trace level elemental analysis. So what we have shown you is that we gave you a good solution to look at low Z elements to high Z elements in geology, and also it can be used for many other applications. And how is possible is because this system is comparable to second generation synchrotron, and also because we use a tunable X-ray source, we use optics, and we can have the grazing angle to characterize